Kubernetes promised us the dream of infinite scalability. The horizontal pod autoscaler, or HPA, is the crown jewel of this promise. In theory, it's simple. As your traffic increases, Kubernetes detects the rise in CPU utilization and spins up more pods to handle the load. When traffic subsides, it gracefully scales back down to save you money. It feels like magic. You set a target, perhaps 60% CPU, and the system handles the rest. This automation is why many teams trust their production environments to Kubernetes. However, this hands-off approach often masks a series of architectural traps that can lead to catastrophic cloud bills, or even worse, total system failure during peak demand. Today, we're looking at why this set-it-and-forget-it mentality is the root cause of the $100,000 mistake. We'll explore the mechanics of where autoscaling breaks down and how to build truly resilient systems. The first major pitfall is the disconnect between pod scaling and node scaling. When the HPA requests more pods, they need a place to live. If your existing nodes are full, the cluster autoscaler must provision new virtual machines. This is where the cost spiral begins. Most cloud providers charge for the entire node, regardless of whether your pods are actually using the allocated resources. If you have heavy pods with large resource requests but low actual usage, you end up paying for vast amounts of slack capacity, empty space on your nodes that you're billed for every second. A sudden spike in pods can trigger a cascade of new nodes, and if your scale-down settings are too conservative, those expensive nodes stay active long after the traffic has vanished. This is how a minor misconfiguration results in a six-figure invoice at the end of the month. Complexity increases when you combine the horizontal pod autoscaler with the vertical pod autoscaler, or VPA. The HPA scales the number of pods, while the VPA scales the size of individual pods. If both are looking at the same metrics, they can enter a destructive flapping loop. The VPA might see high CPU and try to increase pod size, which causes the pod to restart. During the restart, the HPA sees a drop in total capacity and tries to spin up more pods. Then, as the larger pods come online, the HPA sees low average utilization and scales down the number of pods. This constant oscillation creates instability, increases latency, and makes your application unpredictable. The rule of thumb is simple but often ignored. Never use HPA and VPA on the same resource metric. This architectural collision is a silent killer of production stability. To auto-scale effectively, Kubernetes needs to know how much a resource a pod needs versus its limit. This is the requests versus limits trap. If your CPU requests are set too low to save money, Kubernetes will pack too many pods onto a single node. When a traffic spike hits and all pods try to scale up to their limits simultaneously, the node runs out of physical CPU cycles. This is called CPU throttling. Unlike memory, which causes a crash, CPU throttling simply slows your application to a crawl. The HPA sees this high CPU and, ironically, tries to spin up even more pods. But since the node is already saturated, these new pods can't start, or they make the throttling even worse. You end up in a death spiral, where the system is trying to save itself by adding more load to an already failing infrastructure. Autoscaling is not instantaneous. There is a significant time gap between the HPA detecting high load and a new pod being ready to serve traffic. This is the startup latency problem. It involves pulling the container image, starting the runtime, and the application performing its own initialization, like connecting to a database or warming up a cache. If your traffic spikes are sharp, your system will be overwhelmed before the new pods can help. By the time the pods are ready, the spike might already be over, or the existing pods might have already crashed from the load. To solve this, you need to understand your application's time to ready and configure the HPA's stabilization window and select policy to be more proactive, effectively scaling up before the disaster happens. The most dangerous mistake is scaling your web tier without considering your dependencies. Kubernetes makes it trivial to go from 10 pods to 500. But can your database handle 500 concurrent connection pools? Often autoscaling the front end simply moves the bottleneck to the back end. As pods scale up, they overwhelm the database with connections, row locks, and I/O requests. the database slows down, which causes the web pods to take longer to process requests. Because the requests take longer, the CPU usage on the web pod stays high. The HPA sees this and, you guessed it, adds even more pods. You have effectively built a distributed denial of service attack against your own database. To prevent this, autoscaling must be holistic, incorporating circuit breakers and rate limits to protect the fragile core of your system. Kubernetes uses an algorithm called bin packing to decide where pods go. When autoscaling is frequent, it can lead to high fragmentation. Imagine you have several large nodes. Small pods are scattered across them. Because of how Kubernetes schedules pods, you might end up with just enough space on each node for a small pod, but not enough contiguous space for a large critical pod. This results in pending pods that can't be scheduled, even though your cluster has 50% free capacity. This fragmentation forces the cluster autoscaler to spin up yet another expensive node just to fit one pod. Managing this requires setting pod disruption budgets and using tools like dscheduler to periodically rebalance the cluster, ensuring that you're using the hardware you're already paying for. Most teams default to scaling on CPU or memory utilization because they are easy to measure. But for many modern applications, these are lagging indicators. By the time CPU spikes, your users are already experiencing high latency. For a web API, a better metric might be requests per second or request latency. For a message processor, the queue depth is much more relevant. If your queue is growing, you need to scale up now, even if your current pods aren't using much CPU yet. Kubernetes allows for custom metrics through the Prometheus adapter. Moving from generic resource metrics to application-specific metrics is the difference between an autoscaler that reacts to failure and one that prevents it. Instead of relying solely on scaling, build your systems to fail gracefully. This means implementing readiness probes that actually check if the pod is healthy, and liveness probes that don't restart your app just because it's busy. Consider pre-warming your cluster if you know a marketing event is coming up. Don't wait for the HPA to react to the traffic. Manually scale up your replicas an hour before the peak. Also, use priority classes to tell Kubernetes which pods are most important. If the cluster is full, Kubernetes can evict a non-critical background job to make room for a critical user-facing API pod. This ensures that even when scaling fails or hits its limits, your core business remains functional. Kubernetes autoscaling is a powerful feature, but it is not a substitute for architectural planning. To avoid the $100,000 mistake, you must align your pod scaling with your node scaling, resolve controller conflicts, and protect your downstream dependencies. Monitor your slack capacity as closely as your uptime. Remember that every pod you add carries a cost, not just in dollars, but in complexity and potential failure points. By moving from reactive autoscaling to an intentional, metric-driven approach, you can harness the true power of Kubernetes without the financial surprises. Stay curious, keep measuring, and build systems that scale with purpose.